So I'm just going to go offline for a minute and then come back. Some devices need to restart the system, right? So I'll be back. Hello. I think now I'm audible.
Good morning, sir.
Good morning, sir.
Yeah. So we'll begin the class today with perhaps some exercise where I would want to show you how we can do. I'll write a very simple uh, you know, problem. We'll solve it using Excel. So you can see how Excel could also be used to do these things. We'll move to MATLAB in a while, but I'll show you what I mean by stepwise and repeated and iterative ways, and we'll talk about convergence of results and related things today. So I think Excel is a bit slow to open. In the meantime, let me just have some discussions with you. Just a minute. Just share my screen. Yeah. Okay. So Excel is opening up, taking a little bit of time. In the meantime, let's start our class today. So we talked about numerical methods, algorithms, what they would be like actually. So, so talking about numerical methods, and we are going to be discussing algorithms that solve various problems, and these algorithms are number one, stepwise, number two, repeated, and number three, iterative. Okay, so these are like, you could say, the common traits. Okay, then in the class we took an example. We said, let's find out square root of 2. Okay, and then we said, okay, we choose some x naught and we chose it to be 0.5, and then we said that x new is going to be half of x old plus 2 over x old. And before that, somewhere here, let's also say that we take initial x old to be x naught, and then the third step, obviously in this case, would be that x old becomes x new. So initially we choose some initial, we start with choosing some initial value, we call it x old. Then we calculate x new, which is 1 by 2 x old plus 2 over x old. And then whatever is the new value, we assign it to the old value, and we repeat this entire thing. We repeat and iterate. Repeat over iterations. I should put it right. Just a minute. Repeat over iterations. So this was what we talked about. Now let me just see just a second. So, Let me open. So I'm opening up Excel, and this is just some Excel notebook that has opened. So I hope you can see this. Can anybody confirm that you can see the Excel notebook?
Yes, sir.
Yeah.
Yes, sir.
Right. Thank you. So what are we going to do now? This is what we're going to do. So I'm going to write an algorithm. I'm going to do this problem of finding the square root of 2 using this algorithm. And let's see how we do that. And then we can, it will become clear for you what I mean by, stepwise and repeated and iterated. Okay, so let's start. So let's say that, let's say that we've taken x0 to be 0.5. Okay. Then let's call some, so iterations would be this column. Then let's say this is x old. Then let's say this is x new. Okay. And let's also call, we already know, let's say that we know the true value. Okay. So let's say that the true value is given to us, which is 1.414. It's given to us. Just a second. Yeah, okay. Okay, so true value is given to us. We take this as initial value. Let's make a small. Let's align them a little bit. Okay. And let's also kind of talk a little bit about error, since we really need to know where our algorithm is going. So let us call this as error here. Okay, and basically I'll write what error actually means. Error is so error is nothing but absolute of true value minus x. Let's call this basically this. The reason why we're taking absolute is because we're not really interested in the positive or negative value. We just want to know what is the magnitude of the error. All right. So initially I told you that we will. So the first step is that we take x old to be equal to x0, right? So let me just say that this is the first iteration, the first loop, and since x0 is x old, so I take that value to be 0.5. Okay. So once we get that, then we need to evaluate x new. And what is x new? X new is given by this formula, which is half x0 plus 2 over x0, or x0 means x old basically. Right? So let's apply this formula in Excel. So how do we apply formulas in Excel? So what we do is, let me just kind of expand it a little bit so that you can see more clearly now. So what we do is we write a equal to sign. We open a bracket like this, square circular bracket. Okay, so before that, so this is it. So I take this value, I just press this value. So E9 comes because E9 is that cell, plus 2 divided by E9 again. I close it and then I multiply it by 0.5. When I do that, so now I've set up a formula and I'll just press enter, I'll get a value. So this is the value. So this is x new, right? So we can see the formula. It's written over here. Let me just come back again. You can see the formula here. So you can see that this is E column and this is column number E, and you can count the cell number here, which is 9. So what it does is it is taking value which is stored at E9 plus 2 times 2 multiplied by 1 over E9 value, and the whole gets multiplied by half, which is the formula basically. So you get this value, right? So now let's calculate the error. So calculating the error is going to be equal to, and then I'm going to write ABS because ABS is returning the absolute value. So I write ABS, sorry. Equal to ABS. Let's say that the true value is 1.414 minus X new. Always you want to calculate it like this. So this is the error, right? So we have the error. Okay, so this is the first. So this is like at this point of time, the iteration and the step, the step remains the same. But what we have done is that we first assigned this value x0 to x old. So that was step 1. Then step 2 was we evaluated x new using the formula. So that was step 2. And then the step 3 was we evaluated an error, which was basically absolute value, which is true value minus x new. So that is the error. Right? Now, the error is very high. I mean, it's 0.83. So, I mean, that's certainly not going to be making us sleep better. So what we do is we repeat this again. So to repeat this, there was one more step that had to be done, which was that once you calculate the x new, then that x new becomes equal to x old, right? So then that means that now in the second iteration, okay, in the second iteration, what will happen is that this place x old will take the value x new. So I just put F9 here. So now, once this is there, now I need to evaluate x new again, and I need to go here. So now, but the formula is already here. So in Excel, there is this amazing thing. What I do is I just, press it down below, and I come here, and automatically a value comes here. So what actually is happening is that in this cell, it is applying the formula which has been applied in E9, but now it is taking the value in E10 and evaluating it. You can see clearly. So now what I do is I come over here and I drag it further down, and you can see that the error has reduced. And error is now, देखो क्या values है? It is 1.414 minus F10. F10 is this value here. So absolute will give you the error. So this is the second. So you repeat it, and now you see. So now you repeated the same number of steps. The second time you repeated it, and now you've got this answer. And now you see that the error is significantly reduced, but still it is quite high, the error. I think some people have joined, so let me just bring them in. Yeah. So now what we do is we come to iteration number 3. So when we come to iteration number 3, we have already put the formula here. So if I just bring it down here, the x new becomes equal to x old. So this is here. You come over here. So now you see that we are at 42183. Then you come here and you bring it here, and now you see that the error has reduced even further. So in the third step, this error has reduced. So you've repeated the entire process 3 times, and this is what you come, and you've iterated it 3 times, right? Then you come to the fourth part, and now what you can do is that all you really need to do is select this entire thing and just bring it down one more step, and you see that the error has reduced even more, right? Then let's come to the 5th iteration, and if we do this further, then now the error has reduced even further. And let's probably do it for a couple of more times, and let's just drag it up to here. And now you see 6th 7th and 8th. Right? So if you look at it, now there is significant, there is just no change which is coming in the error. So this algorithm that we have used has converged to the value in the 5th iteration. Right? So this is your entire formula. You run it as, you know, maybe a couple of steps more than what would have given you the result, but that's okay. I mean, you're not doing it by hand. A calculator is doing it, and the calculator isn't complaining. So you don't really need to worry too much. So here it is. So you can see what I mean by stepwise, by repeated and iterations, right? Just a second. Somebody's writing something. Sir, how can what was the question? Just a minute. Sir, how we came to know if we iterate this formula to get the true value? I mean, see, the idea is this. How do we know that you need to iterate it? Okay. You know that you need to iterate it because once you calculate the error, you see that the error between the true value and the value that you have calculated is very high. You will keep on iterating it for those many number of steps when till the time you see that the error has become so small that you're okay with the error. See, there will always be an error, right? See, now if there is an error which is 0.000214, is it an acceptable error? To me it may be, to you it may not be, but this algorithm right now that we are using will just saturate at this point. So you can't do any better than this right now, right? So you will stop. And for that matter, 2.14 into 10 to the power minus 4 is a very small value. So you've almost converged. So you know how to, you would actually come out of the loop. So iteration is basically looping. So when I say iteration is looping basically. You keep on moving in one loop again and again. So it's like, how many times are you going to repeat something is what is basically the iteration, right? So I would request people to, join by 10:10 because it becomes difficult for me to keep going back and including people. So if you look at it, this problem that we have done, okay. So if there's a question, you can just kind of, unmute and say it. Somebody wrote something. Just a second. What is the formula for x new? Okay. I think you joined late or something. The formula for x new is this. It is half x old plus 2 over x old. Now, from where did this formula come? That is a different issue altogether. They were hit and trying it 2000 years before. They really had nothing really to do much, I think, in their lives. They were trying to think of something. They came up with this, and this is what it is. So the idea is not how we came to the formula. The idea is how we actually use and what do we actually mean by numerical methods and what is the basic structure of any numerical method. Okay, so now you look at this problem that we are doing it. First, we take an initial value, we assign that value and it becomes x old. We call it x old. Then we calculate x new using that x old value. We calculate a value called error. If this error is satisfactory to us, we could have stopped here also. Is that we know our common sense tells us that error kam se kam 10 to the power minus 3 to hona chahiye. Generally also, there is no thumb rule of what the accepted error will be, but generally you would say that it should at least be 10 to the power minus 3, 10 to the power minus 4, right? Something like that. So we say, no, we are not satisfied with this error, repeat this process again. So to repeat this process, before we repeat the process, we also said that x new will become x old. So we did that. And then we applied again the same thing. We calculated using this new value of x old. We calculated another new value of x new. And then we calculated the error. We were like, chalo, error 0.836 say 0.1115544 ho gaya. So you are happy. We're like, okay, we are converging towards the true value. Let's do it one more time. We did that and we saw that it was again, significantly smaller. We were tempted to go further to reduce the error because that's basically what we always want. And then we got this value here. And then when we then again did it, we got another value which reduced the error further. But when we moved to the sixth iteration, we realized that now we are not getting any less of an error. So that means that this code has saturated at this point and it has come to its conclusion. So you are repeating the same thing again and again and again through the columns. So repetition is happening through the columns, right? You're repeating the same formulas, same steps through the columns, and sorry, you're repeating through the rows. So this is, you're calculating these three things, then you're calculating these three things, then you're calculating these three things, and you are looping through the column. That is iteration. Okay, and you're moving stepwise. You have an x old, you calculate x new, you calculate error, then you assign x new to x old, then you again calculate x new, you calculate error, then you assign x new to x old. So there are steps 1, 2, 3, 4, 1, 2, 3, 4. They keep on repeating a fixed number of times. Let's see what happens if I'm going to change this value here. Let me say that this value is 0.1. So all of this has changed. You can see that. And now what has happened is that you see that now I have moved further away from the value 1.414, and you can see that now that convergence that was coming in the fifth iteration now comes at seventh iteration. See? Now by seventh iteration, it kind of saturates. So your numerical method codes, wherever you'll have to assume a certain value to begin with, will definitely depend upon the quality of the initial guess, right? And the initial guess generally comes from intuition, right? Like for example, I said, let's calculate root 2. Okay. So there is 1, root of 1 is 1, square root of 4 is 2. So we know that 2 comes between 1 and 4. So uska square root jo hoga, wo 1 और 2 के बीच में होगा. So initially I took a value 0.5. चलो ठीक है कोई नहीं. But 0.1 और भी दूर हो गया. So obviously it will take more number of steps. If I make this value, let's say that I make this value 0.01. Now we have not even come close. Now we need to go further, right? So let's do that. So if I take this and let me just extend it further. Now you see that we have come to iteration number 9. We have come to iteration number 10. We have come to iteration number 11. So now you can see that it has taken almost more number of iterations. It taken almost, yeah, it has 11 iterations to reach it, right? So this is, now let's move a little further close to this value. Let's, instead of taking 0.01, let's take 0.2. So now you see that very fast your algorithm is converging to the same value, which is here, and you can see that by third iteration, by fourth iteration, you can see that you've come to the value. Right? Let's instead of taking this, let's say if you take 1.4, and then you just need to do another 2 steps and you reach it, right? So that means that your code is very sensitive, not very sensitive, I'd say. The code is kind of dependent upon the quality of the initial guess. That will always be the case in numerical methods. You have to be smart enough to choose an initial value in case you want to reduce the computation time. Normally, the problems that we do, computation time is not really that important, but it becomes very important when you have large number of variables which are running through and you're calculating the values and you're coming to some conclusion. Like for example, I'm sure that many of you have done, machine learning algorithms and so on and so forth. It takes a little bit of time to train it, right? And to give results, right? Because you have so many layers, you have so many variables, you have several operations to do. It consumes time. So long as time is not important in this problem, it really doesn't matter what initial value you choose. Let's have some fun and probably let's see what happens if I choose a negative value. Okay, let's now this goes berserk, right? You're getting negative लेने का कोई मतलब नहीं है, because square root में हम negative value लेके कहाँ ही पहुँचेंगे. You see that this algorithm does not give you anything, right? Just saturates at this point. So now it makes no sense at all. Why is it not making any sense? Because you've taken an absurd initial value. You're saying square root of 2 is minus 1.4. That is what you're starting with. Now, how can a square root be negative? So now it is up to you to decide. The computer has just calculated the values and given you a formula. Based on the formula, the computer has calculated values and given you the answer. But it should be your common sense that should tell you that negative cannot be the square root of any number. Negative number cannot be square root of any number, and you cannot have an initial guess which is negative, right? So this is like, there are certain things which are like common sense also in numerical methods. The computer doesn't really realize that. No, computer will just calculate whatever you give computer to calculate. It is up to you. So this is also an important thing. Please, keep this in mind. Just because computer is giving you some values doesn't mean that whatever you've done is right. It has to make some physical sense also. A square root of a number is never negative in the real world in which we live in, right? So you can't choose that. So let's not think about it, right? So I hope that this example clearly illustrates to you what I mean when I say that numerical methods are stepwise, they are repeated, and they are iterative. And I hope this example also tells you the importance of choosing a reasonably decent initial assumption, right? There will be times when you have to, assume maybe more than one thing as initial assumption. Like for example, if you're solving a three variable linear system of linear equations where you have like 4 or 5 linear equations, not sorry, you have 3 linear equations in 3 variables, and you need to start your algorithm. So you choose some initial value of x, you choose some initial value of y, you choose some initial value of z, and you just move further. Now, the number of iterations will obviously depend upon what your initial guesses are. Sometimes there are some systems which are not very well behaved. So if you choose the wrong value, they will just go God knows where. We'll see all that when it comes. But I hope that this is clear with this example what we'll be actually doing in numerical methods. Right? So let's come back to our notebook and start doing some work. Right. So I hope this Excel example was clear. You can also try it out on your own systems. You can calculate values of root 3, root 4, root 5. Let's see if you can calculate it with this formula or some other formula. So you can try this in your own Excel sheets. Okay. But let's move further now. So there are a couple of things that we learned, and I'm just going to write them. So things to always remember. Number one, initial guess must be reasonable. Second, keep an eye on the error. Because if the error is increasing or if the error is not decreasing, then that means that your code is not really, either the code has done what it had to do and it cannot do any better, or your code is doing something which is absolutely wrong if the error is increasing, right? So you have to keep an eye on the error. That is very important. And number 3 is that error should decrease through iterations. Okay. If error saturates, then it would mean probably two things. One is that code has reached its uh, utility, I would say, that it cannot give you anything better than this. Okay. Or second is that desired result has been achieved, because the first one may or may not give you a desired result. Right? So desired result may have been obtained. Desired result. Okay, so these are some intuitive points that come into picture when we see that code running. Okay, so you need to remember them. Let's move further. Now let's spend some time on this thing that I'm talking about, error. Now, evaluating error is very important because only error will tell us for how long we really need to run a code. So error is very important in numerical methods. If you're running anything and you're not keeping a tab on the error, that means you're not a good programmer, you're not a good solver of the problem. And that is certainly not the way. And whatever result will come, you're only lucky if that result is correct. All right. So you have to have an idea of how the error is behaved when you're running the code. Okay. So what are these errors? I mean, how do we calculate them? So let's say, so there are two errors that we are normally interested in. I mean, one is, you've already heard these terms. One is called absolute error. And the second term is called relative error. Okay. So let's say that we have a value which is x star. Let's call this as the true value. Okay. Let's call x a as the approximate value. Okay. So in that case, absolute error will be mod of x true minus mod of xa. Simple enough. Something that we have used in the problem that we did. Okay, so this is the absolute error. And the second thing is the relative error. And relative error is x star minus xa divided by x star. All right. So these are two errors. Now the question is that why do we need these two errors, and which one is better and which isn't? So, I mean, it depends. I mean, what kind of a problem you're doing, but the absolute error, relative error is a little better. The reason is that it gives you a better sense of where you are. Like, for example, if suppose your true value is if your true value is 0.1, okay, and the error is coming out to be equal to let's say 0.08, right? Then you'll say that, okay, चलो ठीक है, हम अभी बहुत ज़्यादा दूर नहीं है, 0.08 भी तो comparable है 0.1 के. But if your error is 0.01 and your true value is 1000, then relative error will be even much smaller. So now you know that you're very, very close to the true value, right? So relative error in my opinion, is probably a better way to judge where your code is going. But sometimes you can start off with, you know, putting limitation to the iterations using absolute error. And then you can see if your code becomes better if instead of absolute error, you use relative errors to stop your code. So basically, error is that quantity that you use to decide when the numerical method process will come out of the looping, which means stepwise repetitions will stop when. That question is decided by this error. So generally you'll start the problem, you will say, okay, let's do this step, let's do this step. But before that, in the problem, you'll start for I is equal to 1 to 1000. Suppose you write that, right? Then you expect that by the 1000 repetition, your error would have reduced to this. There is another way to go about it. You can also use something called as a while loop. You can say while error is greater than this quantity, keep on repeating. That is also something that you can do. So you, while is a much better option in these cases than a for loop. The reason is that in the for loop, it could just happen that even after 1000 iterations, you may not have reached the error that you are expecting to be something that will make you happy with the answer that you got. But for loop will always, while loop will be like, while the error is greater than this, you keep on repeating it. So while gives you an exact idea, right? So that is why error is an important thing. I'll write down why error is important. Why error is important. So the error is important because this quantity decides the number of iterations. You know that you have to move stepwise. You know that you have to repeat all the steps. But then the question comes, how many times should I be repeating it? जैसे कि स्कूल में हमें कभी आई डोंट नो वेदर यू हैव डन इट और नॉट, आई डोंट नो दैट काइंड ऑफ पनिशमेंट एग्जिस्ट और नॉट, बट हम लोग जब छोटे थे, हम लोग कुछ खराब करते थे तो हमें टीचर कहती थी तुम लिखो आई विल नॉट रिपीट दिस, आई विल नॉट रिपीट दिस। लाइक मैम कितनी बार लिखें, कभी बार 50 बार लिखवाती थी, कभी 100 बार लिखवाती थी, लिख रहे होते थे कभी। सो द क्वेश्चन दैट एरर आंसर्स इज what is that quantity? It is that quantity, error is that quantity that decides how many number of iterations we'll do. After how many numbers will the entire repetition process stop? That is what error is. Okay, that's why error is important and we need to track it all the time. If you're not tracking it in any code that you've written, that means you've not written a proper code. Okay, that is the importance. Now an important question I want to ask. So there are problems in which you know the true value. Like for example, if I'm saying write an algorithm to calculate the value of root 2, and I said that okay, the true value is 1.414. But there are a lot of problems in real life in which you don't know the true value, right? You're trying to come to the true value. Then in that case, how do you track error? Can anybody think of the way in which we can do that? How would the error tracking happen in that case? When will you stop your iterations? When you don't even know the true value. Here तो हमें पता है true value क्या है, हमने एक approximate value formula से निकाली, हमने दोनों को compare करा, अगर error कम आ रहा है तो ठीक है, बहुत अच्छी बात है, अब हम रुक जाते हैं। But अगर हमें true value पता ही नहीं है, then what will you do? That is my question.
So maybe when the
see the old and the new, the difference that will
yes,
be
sir.
Yes. That is it. Very nice. Thank you. So what we are actually trying to do now is that basically the idea for any numerical method algorithm to run is we want it to converge to a certain value. Whether that converged value is correct or not is a different thing altogether. Like for example, I took the initial value to be minus 1.4 and I evaluated square root and it was converging to some value, right? Let's just look at it one more. So if I've taken it 1.4, I know that by which iteration it is by second iteration it is converging to 1.414 okay, it is converging to this value after second iteration. But let's say that I take this value to be minus 1.4, and now I'm getting all crappy answers, but I know that this is converged. So ultimately what has happened is that the algorithm is converging to a value. We always want a numerical method algorithm to converge to some value. Whether that value has any meaning or not is a completely different thing. Like it has converged. So now once it has converged, I will look at the value and I'll say it is minus 1.4121, and I'll be like, what is this? This is not correct because square root cannot be negative. That means I'm doing something fundamentally wrong. That's the second step. But the ultimate goal of any algorithm in numerical methods when you run is that you're trying to find out something and you're wanting to converge it to some value. So we are not really running the algorithm to find out the real answer. We are trying to find out a value to which the entire process will converge. That is all. Whether that value gives us the accurate answer or not, we have to judge it for ourselves with our common sense, with our intuition, with whatever happens in real life around us, right? So that is a different thing. But the ultimate goal of any numerical method algorithm, I repeat again, is that it should ensure that there is convergence. If there is divergence, the error will increase. But if the error is decreasing, then we are expecting that the algorithm will converge to a certain value. So now the next question that we were trying to answer over here is that how, what happens what happens when we don't know the true value. So answer was given rightly that we try to find out the error using x old and x. But why do we do that? The reason why we do that is that the ultimate goal of, I should not write ultimate goal because ultimate goal is to find the right answer. But let me just write the goal of any numerical method. The goal of any numerical method algorithm is to converge to some value. Okay, so we are only trying to see whether our code is converging or not. So the convergence will be ensured only when the difference between the value evaluated and the value from which it is evaluated is very small, right? So now we define errors like this. So let me call this error as mod of xi minus 1. So this is your absolute error, and let me call epsilon as relative error. So this will become minus xi minus 1 divided by xi. Okay, where, so I'll just write this as this is the absolute error and this is the relative error. Let me also introduce short forms here so that you have no confusion what is EE. So where xi, the value after ith iteration and xi minus 1 is the value after I minus 1th iteration. So we can run a code. We can say that this error, if it is less than 10 to the power minus 5, we'll stop our code. So now that we get a value, ultimately, we are able to say that at least what our algorithm has done is that this converts to a value. Whether that value will have some meaning or not is a different thing altogether. All right. So this is how we are going to proceed with errors. So this was the first. This is the introduction to errors. We'll see what are the different kinds of errors that happen, why those errors come into picture, and we'll do some related numericals. We'll see this in the next class. All right. So I'll end the lecture here today. And if there is any problem, then now you can speak just by unmuting yourself. Please, if there is anything to discuss. Otherwise, we'll just end the class. Oh, okay, great. Then I'll see you tomorrow in a class. All right. Thank you. Bye.
Thank you,
Thank
sir.
you, sir.
Thank 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 you, sir.
Bye bye. Take care. Good day.